and thank you for joining Pete and myself. Before we we crack on with our talk today for Global Azure 2021, we're actually going to talk today about controlling robots remotely with Azure, and we're going to be touching on things like unmanned drones. We'll talk about bomb disposal robots, remote surgery. We're going to talk about the robot arm that we've built with a Raspberry Pi and .NET 5, and touch on Azure and BLAZOR. We're also going to touch on some CI/CD with GitHub Actions, and we're going to make changes there as well. Yeah, it's a pretty fun talk, and you'll actually get to interact with us too. So later on, we'll be popping out a URL that you can go to and get involved in some remote control of the robot arm that we have as well. So, first and foremost, like we say, we are going to be talking about the controlling robots remotely with Azure. But we are part of Global Azure over yesterday, today, and tomorrow. If you are taking part, please feel free to take a quick scan of the QR code on the screen now, because you can get some free swag as part of Global Azure as well. With some, I think they're engine tokens, as far as I'm aware, and obviously
they're virtual badges. That's as much
badges.
That's they're just cool.
Yes, yeah. And some virtual backgrounds and that kind of stuff too. So, I guess if you've already been to our channel before, you'll probably know who Pete and I are, as well as the whole host of other folks we have involved with Azure Live. But I am Liam Gulliver. By trade, I'm a DevOps consultant, cloud solutions architect, and systems engineering delivery manager for MMT Digital here in the UK. I was software dev, and specifically in .NET, and then moved my way through different roles, always doing DevOps type things as well, until I landed in the role that I'm in now. I also organise a meetup here in the UK called DevOps Knots, and we talk about all things DevOps, whether that's Microsoft related as well, or Amazon or Google. We do that on the last Tuesday of every month, and we've got a really great meetup coming later this month as well, so keep an eye out for that. I'm also one of the hosts of the Agile Engineering Podcast, where we talk about all things to do with software development, from leadership all the way through to concepts. We might talk about things like Agile and that sort of stuff too. And obviously on the channel we're on now, one of the creators and hosts for Azure Live and Azure After Dark too. Pete, do you want to tell folks who you are?
No, nobody wants to know who I am. I am an IoT consultant generally, but I'll do anything IT. I've been doing this for years, actually, for myself for over a decade now, and professionally for over 2. So just like Liam, been doing this for ages. I also run Knots IoT, an IoT meetup that's virtual at the moment. And I co-organise with Jess White, .NET Knots, and I'm part as well of the Agile Engineering Podcast and the Azurist Twitch channel, where not only do we do Azurist stuff, but we've got the IoT Live show. And I'm a Pluralsight author and a Microsoft Azure MVP and Microsoft Certified Trainer and Code Club organizer. Yeah, I like to keep myself very busy, it seems. And I've got 2 small girls, which is one of the reasons why I like the outreach part of what I do, the community side of what I do, and certainly code clubs and being a STEM ambassador and stuff like that speak to that as well. So it's all good. And today we'll be talking about some IoT goodness, which is my bag, and we're going to mix it with Liam's bag of DevOps goodness. So
we're regularly told, Pete, aren't we, that we're 2 of the busiest men in tech.
Pretty much, it's true.
Cool. So, what we're going to be doing over the course of the next hour, so we're going to take a quick look at our project and its architecture. We're looking at using a Raspberry Pi for a lot of this, and .NET 5 in BLAZOR, and we can use app services and all sorts of great stuff. We're going to talk about how the robot was built. We're going to talk about how we built a UI for it. Then we're going to make a quick change. We're going to deploy that via GitHub Actions, and we'll talk you through what that pipeline is doing too. And then, folks, we're going to let you play with the robot. And then we've got a nice little special edition at the very end, which isn't on this list. But if you were at the Welsh Azure user group last night, you would have got to see that in action too. So, project and its architecture. Now, the sort of technology that we're going to be using today is super rudimentary in terms of, we can run it on Pete's desk. There is a robot arm sat in Pete's house right now that will be controlling from all around the world.
Shh, it's not rudimentary. It's very complicated.
Yeah, sorry. Yes, absolutely. We should be trusted to build the sort of things that you can see on the screen right now. But what we have is kind of like a hello world version of some of the technologies that can power the things that you see in front of you. So you have unmanned aerial vehicles or combat drones or any of those things. Mars rovers, remote surgery robots, bomb disposal, and that kind of thing. We could go as far as saying, well, if we put a little bit more time into it, you could control them with an Xbox controller or any of that sort of thing. And what we're able to demonstrate here is that we'll have real-time communication between a remote interface and this robot. And we'll talk a little bit at the end about future applications of stuff that we're thinking about doing with it, and that kind of stuff too. So let me just switch over to Pete, because he will be going through the next section. Let me just make that full screen, Pete. Sorry.
Cool. Yeah, we'll talk about .NET, GPIO, and all of these good things. So if I can click on this and make it do something. Normally installing something like .NET on the Pi is perfectly doable, but there's lots of steps involved to get it to work, and it can take a while, and it can be a bit of a blocker if you've not spent much time with Linux in particular. But I mean, most people, at least in a drawer, have got a Raspberry Pi that's just sitting there doing nothing. So this is definitely a good way to resurrect your Raspberry Pis. But if you've then got to spend hours trying to figure out how to install .NET on it, then that might put you off a little bit. So I made a single line install script that you can see on the screen there. And that GIF underneath will show you sort of all the steps that you would normally have to go through yourself that I automate automatically. That's kind of how automatic works. But yeah, you just do a reboot at the end and you've got .NET 5 installed on your Pi up and running. So it's takes all of that barrier away.
Yeah.
What we've got with .NET is this SYSTEM.DEVICE.GPIO NuGet package, and that gives us access to all of the pins down the side of the Pi that you can see on the top of the Pi there in that image, which break out things that let you control LEDs and read buttons. But onwards from that, we can drive serial interfaces, UARTs and SPI and I2C. And we can drive things like servos, which is lucky for what we're doing today, with PWM, pulse width modulation. And we'll come back onto that. With the one simple package, it's quite a straightforward package to use. And you just install it from your normal .NET add package command and you're off and running.
It's a regular NuGet package, isn't it?
Yeah, it's what it is. That's exactly what it is. So, and obviously, if you're in Visual Studio, you can do it with the NuGet package manager in there. But you might as well just do it on the command line like I do. It supports other boards as well. If you want to go your own way and don't want to use Raspberry Pi, then there's Odroid and Hummingbird and whatever they are. But just use a Raspberry Pi because they're just the way that we need to go.
Why is that? Why would you choose a Raspberry Pi, say, over a Hummingbird or a BeagleBoard?
Support. The community around the Raspberry Pi and the development that the Raspberry Pi Foundation put into that board and the iterations of that board just mean that that's where the gravity is. That's where all the developers are going to be, and that's where Microsoft will test their libraries. So the .NET library is regularly tested on an actual Raspberry Pi.
That's pretty cool. I didn't know that.
Yeah, so they know that people are using this. What interests me is that they don't make it easy for you to install it. It's taken someone like me to create that single line install script. There's no apt-get. for not on the Raspberry Pi. There is for like 64-bit Linux if you want, but for regular 32-bit Raspbian, and I know it's Raspberry Pi OS these days, and there's a 64-bit version of it. But even so, this is probably the simplest way to get there.
Yeah.
GPIO, if you don't know, that's general purpose input output. And as I say, that's all these different pins down the side of the Pi. And each one of those pins is numbered, with the square pin at the top left being pin 1, and then opposite it is pin 2, and then below is 3 and 4 and onwards like that. There are 2 different numbering schemes that we're going to be able to use. The board numbering scheme, which is the one I stick to, are those numbers I've just read out, 1, 2, 3, 4, 5, 6. But there's also the BCM numbering scheme, which is referring to the BCM driver chip for GPIO. Don't use that, because then you've got to convert from that BCM number back to a pin number, and then count pins as well. So just stick with the board numbering scheme, and you'll be all happy. We've got a little servo board called a Servo 6 board in between our Raspberry Pi and these little servos, and I'll explain what servos are in a minute. But we've got this board because you can't just plug a servo into a Raspberry Pi. Well, you can, but a servo can take about 300 milliamps of current, and a Raspberry Pi pin is only really rated for about 30 milliamps.
Oh, so right, okay, I didn't realize that either.
Yeah, so although it might look like it's working, you'll quite easily damage the GPIO pins on your Pi if you drive these things direct.
So that would do, because then that's because of the power draw of the servo rather than anything else.
Exactly that, yeah. So, I mean, the initial inertia, that amount of action needed to turn the servo to begin with, is where the majority of that power will come from. But if you've got something on it...
Right, okay. So like startup.
Yeah, exactly. Yeah, that's right. As it's moving, it's probably not too bad. But certainly if you've got something on it and it's got to try and move it from a stationary position, then it's going to draw a lot more current. So, and obviously, if you've got any questions during this, then use the chat. We're both looking at that chat. I've got the Twitch client open beside me, so by all means shout in there if anything's unclear or you want anything explaining more. We've got plenty of time the way we do this talk. So yeah, I've got this little servo board in there, and that, as you'll see in a minute, if I sort of go across a little bit, we've got a fuller circuit here. So we've got a battery pack there connected to the servo driver board, and that just means that all of the power just comes from those batteries and not from the Pi. And all we do on this side is we just connect the servos and the power to that end. And over on this end, we connect the Raspberry Pi out. So we've got that black wire there is the ground pin. I don't like the labeling on this board. That's the only thing I don't like about it. That ground pin is that one. Then you've got the channel 1, channel 2. So we can drive 6 different servos, if you will. And the blue wire there is channel 1. And then the green wire is channel 2. Now, they're the 2 hardware PWM ports on the Raspberry Pi. And by that, I mean that we can just tell those 2 PWM pins what to do, and they will do it sort of underneath what happens with the operating system. Now, you'll see that there's a white wire connected there, and we're connecting that one and using it in a software PWM mode, which happens above the operating system level. Now, the difference between these 2 things is that now we've got to try and deal with the operating system to get that pulse to work properly, and we'll come back to those in a minute. By the way, this is the go on.
Okay, if you just drop back a slide, Pete. Now, I think I'm sure I've asked this question before, and I have, being completely honest, forgotten the answer.
That's all right. It's a learning opportunity.
So, in some of the close-up images, of the circuit, we've got where it says we're using a Raspberry Pi 4, and some say we're using a Raspberry Pi 3. Does it matter?
3 or 4 is fine. You can't go further back than that. You used to be able to do it with like a 2B plus, but I think the support has dropped out for some reason. Something's happened. There's been a reversion in their support. So 3 or 4 will work.
Is that more of a software constraint, or is that due to the GPIO constraints potentially?
Sort of. So the operating system knows which version of processor you've got in there. And I think the 2B plus is perfectly fine, but I think the software, when it looks for the supported processors, has dropped that line out of it that says this particular processor is supported. But it does work. You just need to make sure that you've got, I forget what it is, there's a certain version of the ARM processor, ARM V7, I think it is.
Okay.
And I think the 2B plus has got that, but its ID number for that processor isn't in the listed supported processors for some reason, even though it does work. I think that's what it is. Somebody can correct me in the chat if I'm wrong on that, but that's kind of how the basics of that's working. But I use a Raspberry Pi.
I will take your word for it, because this
Yeah,
is your
well,
expertise area.
go and look it
This part
up
of it.
if you can find. You'll see in a minute when we show the images. I'm using a Raspberry Pi 4 down here because it's just better. I think yeah, and you can tell the difference between those two because the Raspberry Pi 4 has got the dual HDMI outputs. The one you can see in the image there is a 3B plus because it's got a single HDMI output. So that's the easiest way to tell. So on this page though, that's the robot that I've used. And actually, there's a GitHub repo that I'll link to in the chat here in a minute. We really must add that to the slides for this.
Yes.
Well, I don't know why we've not done that, but either way.
Also remember, Pete, that we do have a link to the app in one of the slides as well later, so we won't need to put that into the chat necessarily.
Okay, well, we can for people to click on anyway. But yeah, so I built, printed and built this one, and it took ages. And I didn't have all the right nuts and bolts either, so I was scrabbling around for nuts and bolts, and it's rickety as hell and falls over and everything, which you'll see in the demos. But Cliff Aegis, so I know he's in the chat here, him and his son have made a far better and simpler version of this robot. And I know Johnny Chips, who's also in the chat, he built the V2 version of this robot, which has got bigger, heftier servos on it.
Yeah.
So that's great, but Cliff Aegis's one that him and his son developed is fantastic because it's just got 3 or 4 servos, and you screw the servos into the parts, and that makes the robot. And it takes about 25 minutes. It took me an hour and a half, so it's a lot better. So that was that control. This is a little bit about servos and explain how they work. So servos are based on PWM, pulse width modulation. So you modulate the width of pulses to be able to drive the servo. So like short pulses here, that will send the servo one way. Medium pulses will put it in the middle, and long pulses will put it on the other side. There's a little bit more to it than that, but that is the basics of how a servo is driven. Now, you can see those pulses have to be exactly the right width to get to exactly the right position in that. And this is a 180-degree servo. There are 360-degree ones as well.
So is that why? So when we have our control, which everyone will see on screen shortly and be able to interact with, when we're setting the angles, that's basically setting the width of the pulses.
Yes. Yep. Right. Exactly that. Yep. And so they kind of hover where they are depending on what that pulse is. They're kind of constantly moving, if you will. But it's just, you can sort of notice it if you get it in just the right position and it's kind of leaning on the servo motor, it buzzes. So this is what I was saying about the difference between hardware and software PWM earlier, in that if you don't get those pulses the same width all the time, then it's going to be jittery. And if you're trying to move and make those pulses go smoothly between 2 angles, if you've got an OS underneath that, timing is generally quite difficult. So software PWM is never as good as hardware PWM. And certainly when I know Cliff, again, he was in the chat here, he said, why don't you just use a PWM board? And you can get little serial I2C PWM boards that'll have like 16 PWM drivers on there, and they just do it. They're fantastic, but I did it this way because I wanted to introduce people to the SYSTEM.DEVICE.GPIO, and there's a device bindings library as well, which we'll talk about shortly. So before we go on to looking at code and all of that sort of stuff, we'll talk about sort of the other tech that we're going to add to this along the way. In fact, Liam will at this point.
I shall, yes. So let me just move that out of the way. Just make sure we're on the right slide as well. So yeah, so we built a UI. Now you'll have seen robot arms in the past and that kind of thing, where people build some really quite cool, to be honest, sort of physical controllers, I guess, Pete. Like, so where you can have levers and all sorts of stuff, and it's cool. I'm not gonna lie, I like that done thing. But what we've done to enable the remote control for everybody in the audience here to take part in what we're doing, and physically manipulate the robot arm that's sat on Pete's desk, we built out a UI, or rather, Pete started it a UI that's built on BLAZOR and Signal, and that was just for, I think you built it, you started it out, Pete, didn't you, to basically just give you a UI to play with, to control the arm, right? I think.
Yeah, well, exactly that. I mean, this was before I realized about things like Uno platform, which gives you UI on a Pi, So I needed just some way of doing it, and I didn't want to use the console to be able to control the robot arm because it's rubbish. So
Oh yeah, I forgot about that. Yeah.
yeah, so that'd be terrible. So I wanted something with sliders on it, basically, which we'll get to in a minute. And obviously that meant that I needed to do it with a BLAZOR app, because the alternatives were terrible, like GTK and Mono or something, Mono Develop on a Pi. And I've tried that and I didn't like it. So
No. So Peter already made some fairly good choices around what we wanted to do, around the tech side of things for what we wanted to achieve. And in fact, this talk kind of came about from Pete and I chatting about it when we said, well, I wonder if we could just do this multiplayer effectively. And so we made some changes and adapted it to do that. So let's just quickly take a look at what BLAZOR and SignalR are if you're not familiar. We have BLAZOR, which is a .NET based front end side of things. You know, it allows us to write fairly modern web apps or PWAs entirely in C#, but we can also do interoperability with JavaScript as well if we need to, and it compiles down into for the most part, I think, WebAssembly. In fact, if you've seen any of the stuff Pete and Jonathan and I have done, we do a lot of work with BLAZOR and specifically around the WebAssembly piece, so that, you know, we don't have to so we didn't have to learn React, basically. I think it's where we're coming from. And it's all familiar territory as well, because going all from .NET backgrounds, we're writing Razor, which has been the de facto kind of out the box stuff for MVC for a number of years now, and you can also run it as part of a server side thing or like client side WebAssembly. And we tend to lean more on client side WebAssembly things for what we're doing. Like you'll have seen our Git watcher, it's all client side because we've gone completely serverless there. But for this, we're using server side. Because we're actually hosting our SignalR hub as part of it, but we'll come to that in just a second as well. And again, there's lots of support for this in most modern browsers and loads of libraries out there. And you can knock something up pretty quickly from there. It's also no longer like a beta project. I think it's been GA now for a good few months, and I believe again, correct me if I'm wrong, I think it's going to be LTS in the next version of .NET.
Yes, yeah, because .NET 5 isn't LTS, is it? It's .NET 6 is going to be LTS. So yeah, quite a good point that. Although the version in .NET Core 3.1, that'll be LTS, of course. So, and I think that was a GA V1, but I don't think client-side WebAssembly stuff was GA'd in that. I think that came in .NET 4.
It might be LTS. I think BLAZOR itself became LTS in this version, but the rest of .NET isn't.
Yeah.
In .NET 5, I think, because they're separately on it. But yeah, so one of the things that we need to do with to basically make this multiplayer or even single player, and I don't know why I picked these terms, but that's what we're going with, is real-time communication. And the way we're doing that is using SignalR, which again is an open source project. It's created by David Fowler and Damien Edwards. It's a Microsoft product, and it lets us do this bi-directional real-time communications. If you go to, I think there's a bunch of already pretty good examples in Microsoft Docs, or you go to my blog, which we can put a link to somewhere, where I build a real-time chat app with BLAZOR and function apps and the Azure Signaler service, which is the serverless option, where you can take a look at that as well. And it is lightning quick too. And you'll also see a little sort of bonus demo towards the end of this that it really enables us to be able to do stuff with multiple types of interface and not just web apps. So, Pete, this is back to you for the firmware.
Oh, was it already? I was just going to send a
link
to the GitHub. I'll do that in a minute then. So I don't think I need to present anymore, do I, on this? So I can.
No, I'm just going to make the screen bigger for you, so it's on the stream.
Good. Good. So normally, this version of the talk is one that Liam and I do together. Now I've got a version that I do on my own where I basically walk through a workshop, beginning with Hello World for LEDs and resistors and buttons and stuff like that. But the code is quite important. But I'm not going to step through all of these different steps. But it isn't. I think it's important for you to see what those code steps are, because it will give you some sort of a grounding about where these pieces fit together. So I start with this flash LEDs one. Now, if you've ever done any IoT, Hello World is flashing an LED. That is just what it is. And then you read a button, and then you're connected to the cloud, and to Cliff Agis's disgust, you send up temperature and humidity readings, and you're happy and smiling, and you go and drink beer and congratulate yourself. But we always start here with an LED nonetheless. So we bring in this NuGet package I mentioned earlier, the SYSTEM.DEVICE.GPIO. I've also brought threading in because I need delays. Down here, I always leave this console write line Hello World in my IoT projects, specifically for the next particular piece of code where it just doesn't do anything until you press a button. You just don't know when it's ready. So you could be sitting pressing the button and thinking it's not working, but it's just not started up yet. So it kind of just gives you some idea of what's going on. So I'll leave that in. Next, we've got the GPIO controller line that we're spinning up here. So we create a new GPIO controller. This is what does the heavy lifting of this whole project to a degree. And this is where we interface to all of those pins on the Raspberry Pi. And we're passing in this board numbering scheme, this pin numbering scheme rather, of board, which we mentioned earlier. So you can either have board or BCM. Just stick with board.
It might sound like a stupid question, Pete. But is that just a standard numbering scheme regardless of GPIO?
Well, every IoT device will have a board numbering scheme. So they will have a set of pins, but they will have numbers on them that will go from 1 to whatever the number of pins is. The BCM one, they're all scrambled up because it's just where the original creators decided to surface them on those pins. So, I mean, if I do a dot, it might or might not. No, it's not going to give me any IntelliSense, but there is a .bcm that you can do there instead. So just don't do it. Just stick with the board numbering scheme and do yourself a favor. We can all count. We don't want to have to do conversion. It's bad. So next, I've got a couple of variables here, specifically a pin. And I've got this LED connected to pin 10. And with that pin 10, I can open a pin using this GPIO controller, and I can tell it to be an output. So we're going to drive an LED here, in fact, on line 25. We do a controller.write, and we send a value of high to that pin, turns the LED on. And then we have got a little wait, 300 milliseconds, that's what that 300 is. And then we go low, and then we wait again, and then ad infinitum, we go round in that loop, flashing the LED on and off. And once you've got to that part, that's Hello World, as I've just said, for IoT. Now we've proven that we've got C# running properly on the Pi, and we're able to interact with the GPIO on there. So that's great. And at the end, I just make sure I release the pin again in case you need to use it for something else.
This is the bit why this is why I get involved in this part of it more with what Pete's doing, because this, in my opinion at least, is the easy bit. It's the actual electronic circuits bit I struggle with. That's why I'm friends with Pete. That's why he's in
Lego though. The electronic circuits bit, it's just Lego. It's like a physical representation of the code almost. That's kind of how that feels. I like both. I mean, I didn't do like a CSA level or a CS degree. I did electronics and electrical engineering because I wanted to have this synergy between the hardware and the software. I love that world. So I've been doing this since 1995, essentially, when I was at college.
I was still in school then, Pete.
Yeah, okay. That's
primary school. But
I was getting drunk at that point. And many other things that we won't go into. So what I've got here is a bunch of branches, and I stepped through all of these branches in the full version of this talk, and I still do that here, but I'm just not going to run it up. So the next thing you want to do is read a button. Of course, you want to make sure that you can not only output to something like an LED, but also read back in again. Everything at the top's the same. Still using this device.GPIO NuGet package. Still using the GPIO controller. I've just got an extra variable here for a button, for the pin that I've got connected to the button. And then I'm creating this, opening this button, and I'm doing an input pull-up. Now, it's quite important, and if you remember, for those that were savvy enough when they were looking at that circuit diagram earlier with the tiny little circuit, the button is connected directly into the Raspberry Pi in the setup that I've got here. And if you do that with what's called an open collector input, that input will actually just float around. you need to actually tie that input off to a specific high or low so that you can get a proper reading. So if you tie it high, then you'll get a 1 when you're not doing anything, and if you press it, then you get a 0 or a low or a false, and the other way around, depending on how your logic is. I've decided that I can use a little resistor inside the Raspberry Pi to pull that pin high normally. So what that means is when I press the button on the outside, then that connects, because of the way I've got the circuit connected, that connects that pin down to ground and makes that input go low. So it's just sitting there high at the moment, and I press the button and it goes low. That's quite important because it makes the logic seem a bit backwards, in that if the controller .read here, so I read that button pin, is false if it's low, then I turn the LED on. So it kind of just seems like the logic's a bit reversed. And if it's not pressed, then I turn the LED back off again. And that's as much as you need to do. You just read the pin. Now, there's a certain amount of debouncing you can add into all of this and everything, obviously, if you wanted to go that far. But for demo purposes, turning an LED on and off, I don't care about debounce. I'm not going to see it on the LED. But you can absolutely do some form of debouncing here if you want. So once you've done that, then there's a bunch of other stuff that I would normally step through, but they're the two main parts. And if I step back to the main code here, so let it do that. It'll take a little while because that's a fair jump. Then we can start talking about what the code is doing as far as Signal R is concerned. So Signal R is a hub at the middle of a communications layer, essentially. So you've got this hub that lives on the server side of a project. Now we've got a client application, a WebAssembly application, but it's backed by a server still. You can do this serverless, and we did this on Azure-ish Live, where you use the Signal R service, but it's actually reasonably complicated because you've got to go through an Azure function for authorization and stuff like that. Whereas if you deploy what's called a hosted BLAZOR WASM app, then you get 3 different parts to it, and I'll actually show you those parts in a little minute. But what I've also brought down into here is this IoT.device here. So this isn't that same device library, that NuGet GPIO library I was talking about earlier. This is another NuGet package called IoT device bindings. And this is a bunch of somebody else's code that they've nicely written for us that can interface with a whole heap of components, IO expanders, temperature and humidity sensors for Cliff specifically, and also servo motor control. So I mentioned about how servo motors work with these different degrees of movement being based on the pulse widths. We don't have to deal with that. All we want to do is say move to a certain angle, and that's all we want to deal with. So this is one of the benefits of using the IoT device bindings, is that somebody's written a servo control library for us, which is dead nice. I'll talk about those in a second. It's at the bottom of the screen. But I'll also bring in a Signal R client. And you'll see this reflected again when we look at the website. So this is the part that's going to talk up to that hub. And we're going to send and receive messages. In fact, specifically on the robot, we're only receiving messages. And this will need that for part of Signal R, HTTP. Here I've got the hub connection because I need that to be a global variable there. That's why it's sitting outside of that program level. Next up, we're creating these PWM channels. So again, we're driving the servo with pulse width modulation. So this uses that SYSTEM.DEVICE.GPIO NuGet package. That's where the PWM stuff is built into. And we create a PWM channel, and we pass in a chip number. There's only one chip on the Raspberry Pi. And we pass in a servo, a channel number for our servos. And there's only 2 channels, 0 and 1. And we also pass in a frequency that I've just left at 50 because it works. Once we've created...
Is that just I mean, the frequency wise, is that a general default that you'd go towards, or does it I guess what I'm asking is, does it depend board to board?
Servo to servo, yeah.
Right.
You might need to fiddle with these, and you can look at the specs for your servo if you can find them. I'm using the cheapest, nastiest servos. I think they're called 10G servos, and you can buy about 6,500 for about a penny. It's not quite like that, but they are cheap.
Yeah.
Multiples for way less than £1. But they just work, and if they blow up, you just pick another one up and use it. So it just makes a lot of sense.
We did that, didn't we?
Yes, you did blow it up. Yeah. If you go up against like the end stops too much and you start driving too much current through it, then they get hot, and then they overload, and then they just stop working forever. And you can strip the gears, which is actually what we did. So once you've created the PWM channel, you can pass it into this new servo motor control, and this is the one that's in the device bindings. So we pass in the PWM channel, and we also pass in the number of degrees that this servo supports. We're using 180-degree servos, but there are 360-degree servos, so that's what that's for. And then there's a minimum and a maximum pulse width here as well that you can pass in. And as Liam said there a minute ago, you might need to fiddle with these to get your servo to go up against those end stops. I just left mine as they were pretty much, and they just worked. So that was nice. So I've created one there, and we create another one virtually identical, just we're passing in a different channel just here. But this down here, we're creating this software PWM channel.
Yeah.
And the difference with this is that this IoT device bindings library is creating and managing this pulse width itself, and it took me a while to figure it out, and I had to go in the Discord for the IoT device bindings group and ask them, and they said just stick this true after you've created it, and it puts this timer into high precision mode, which means that instead of, as Johnny Chips and I found when we were doing it, and then Liam again when we were preparing this talk a while back, is that if you don't turn that on, then you get a really jerky movement. It's really bad.
So you would have seen on like the on the robot arm, we've got for lack of a better description, like a grabber. And when we didn't have this as true, you had to basically move everything, all of the settings for, and you'll see when you get to play, we have a slider. You have to move it all the way to one end or the other for it to just open or close. And there was no granular control; it was just open, close.
It's on off.
Yeah. And that, I think we made it fall over doing that as well, didn't we?
Yeah, it wouldn't surprise me. So that's what that's doing there. So, and once you stuck that true on there, it actually works really well. And in fact, in some ways, I think it works better than one of the other servos that I've got, oddly. It's just concentrating on it more, I guess. But you pass in, it's very similar. So you've got a duty cycle, and you've got a frequency, and that's the pin number just there, and then high precision mode. Once you've created it, it works just like the PWM channels above. You pass it into the servo motor, and off you go. While I was fiddling with it, I ended up with different values there. It makes no odds for what we're doing here.
Yeah. Then
you start the servo motors up, and then I can forget about them for a minute, because the next thing I do is create my connection to the Signal R hub. Now I need to change this address in a minute, which I will do. But essentially it calls into this chat hub address, which is just an address you've mapped on the server that calls into just a tiny little hub class that deals with the communications in and out. And
it doesn't have to be chat hub either, does it? It can be basically anything.
Yeah, you can just map that to whatever you like. Absolutely. And in fact, I think, didn't we have to do something like that for the Signal R service in Azure? We had to do some form of mapping, didn't we? So something like that. You'll see here on line 52, I've had to do this dangerous accept any certification, any certificate validator, because when I was connecting to my PC, I was coming up with certificate errors, and I tried all sorts of suggestions. Some people said that when you went to .NET 5, you had to reset a bunch of client certificates and stuff. I tried all that, didn't work. This was the only way I managed to get around that. It might be fixed by now, but don't do this in production. But for what we're doing, it's perfectly fine. We don't need to worry. I've also got
they
this.
Definitely don't do that on the Mars rovers.
No, they probably wouldn't. No, nefarious people would be moving that thing around before you know it. Maybe that's why the helicopter's not working. I don't know.
Yeah.
But I've added this with automatic reconnect. One of the reasons, for that is that part of this demo in a bit, when it's Liam's go again, we'll be deploying a new version of the web app, and it means that the Signal R hub will disappear and come back, and that's what that line will let us do. And then we build it. Then we've got some stuff here with .on. Now, if you've ever done any Signal R and you've ever done a tutorial that takes you from start to finish, the first thing you will have done, like Hello World with a Raspberry Pi and an LED, is a chat app in Signal R. That is the ubiquitous Signal R demo. In fact, it's any WebSockets demo, really. You will do a chat app. And I've taken that chat app and usurped it for my own purposes. So you'll see I've got a user, which would be normally the user typing into the chat and the message that they would be typing. And I've taken the user as the servo number that we want to control, and the message to be the angle. So it's quite simple. If the user is servo 1, then I take their message and I move that servo 1 motor to the angle in the message. And I do that for all 3 servos. And then I've just got a tiny little routine down here that just tidies it up a little bit to do servo.right angle and the angle that we want to go to. And I mean, that's the robot code essentially done. But what we've then got is the code for the website. And I'm not going to go into any great detail with that code because it's reasonably complicated. But up here in the client, in fact, if I minimize all of this, we've got a client, a server, and a shared on the left-hand side. So this is the thing I was mentioning earlier. So the client is the WebAssembly part. That's going to be on your machine, on your phone, or on your desktop browser. The server you will host in like an ASP.NET web service, web app rather. So that's where the hub is going to live. So the client stuff is dead simple. There's not much to it. If we go to pages and index, then this is basically a vanilla .NET new BLAZOR WASM -- hosted website. There's not much to it, but I've got some. If I close that down again so you can see, we've got some of these sliders, and I'm using the Matt BLAZOR open source library of UI stuff, which is dead good. If you've not seen that before, go
material UI type stuff, isn't it?
Yeah, it's really good and free, which is great. But it had sliders, and they're easy to use, so that's why I'm using it. And I bind some properties, servo 1, servo 2, and servo 3 below. And there's some other properties on there that we don't need to worry too much about. But needless to say, when I move the servo, it interacts with these properties down here. So servo 1, and it sends this message out through a hub up here. Now, if you remember from the robot firmware, then this is virtually identical down here. So we've got this hub connection. We build that with a URL, and we've got this chat hub. The only difference is that this is going to be connecting to its own server. We've still got automatic reconnect and a build, but when we receive a receive message, then we just do a bit of control just to add it to a list of messages so we can actually see what's going on, and then we start it up just like we did. Apart from I start it up as async down there. Then
just while you're going through that, Pete, Johnny's asked a question in the chat about what would he need to look at to add an authentication mechanism to the robot arm firmware to talk to the chat hub, i.e. secure my website with Azure AD Modern OAuth.
Yeah, I keep asking about OAuth to Jonathan and Liam because I know nothing about authorization, certainly for any websites and stuff. But I know on the SignalR service, then there's a whole process of authorization you've got to go through, isn't there?
So I guess what we did with GitWatch is probably closest, I would assume. So I guess as a quick example, what we have with GitWatcher is we have a front end, which is all BLAZOR WebAssembly, and we don't have any of the server piece that Pete's been showing us here as well. And we use the Azure Signaler service, so we use it all serverless and everything else, but that's also something that we need to authenticate to. Then what we have for our backend processes is we have a bunch of function apps. So we don't actually use this .NET Core auth that Pete's showing us now. You can go down that route if you want to, but what we do to say completely serverless is we use a functions proxy, which the front end will authenticate to with. I think we just use cores to limit where the calls come from, and then on the functions proxy, we then have function keys for each thing that it will forward on to that way instead, and any auth between the backend and SignalR happens with the function app instead, rather than anything happening in the client. It seems to work for us for what we're doing because we're not doing anything massively complicated. But like Pete's got on the screen there, you've got jot auth and all sorts that you can do if you really want to. It depends on your security needs.
Windows auth, which should be AD essentially, wouldn't it? I guess.
Yes. Yeah.
I'm guessing claims based. So I've just put a link to that in the chat. What Pete is showing is cool, and yes, what you're saying makes sense. Tar, yeah. So I think this would be it. And looks like you can kind of just turn it on and add a few bits, and you're going to be off. Yeah. I mean, I'm guessing that any form of certificate-based authentication would be the best way. And what's that, claims or whatever they call it? But
yes,
something like that. authentication and all of that side of it is generally. I mean, I'm an IoT guy. I'm not supposed to know anything about security, am I? Surely.
Yeah, you don't do security, Pete. That's
No, I don't do that. No.
I'm just conscious of time because we've got about 15 minutes left.
Oh, that's plenty. That's plenty. So I've finished with the web code virtually. So here, those properties look, and we just send out survey one, and we send out the value of the survey, which is fine. But as I pointed out earlier, we've got a server side, and in hubs here in Chat Hub, this is where we're dealing with sending those messages out. So it receives a message, user a message, and it just sends all of that to all. Actually, on the version that we've deployed onto the web, we do all other clients because it was confusing the situation when we did it to itself as well.
Yes, yeah,
We had to fix that. That was quite easy, and it just sends that out. So, funnily enough, Cliff Aegis and I ran a version of this for the Microsoft garages around the world, globally, and all of them, I think, came and there was people represented from all of the places. But at the end of that, we had everybody get their robot connected to this same service, and we could move them all simultaneously. It was pretty cool, actually. It was, as people keep saying sometimes in the chat when we do this, it's very Skynet, that is. So yeah, that was pretty cool. And they've got a bunch of stuff you have to do in the startup.cs file to configure SignalR, but it's not hard, and all of the tutorials will take you through that. So that's not particularly difficult. But what we really want to do is do the cool playing with, because we've done a lot of talking there, and I think it's time that we actually showed people what it was we were talking about. So you can switch over and you can do your bit of the DevOpsy part while I'm inserting stuff onto into my.
So you start the firmware up and stuff.
Yes, I can do all of that and get it all running.
Yeah, cool. Yeah, so whilst we are on that topic, I'm going to do the continuous deployment piece. So what we actually have, I think it's actually here anyway. If I go to GitHub, what we've got is I have this particular fork from Pete, where if I just zoom in a little bit here as well, because it's going to be tiny. We store everything in GitHub, and you can go and look at all this code that we have here and pull it down yourself and build your own robot and everything. In fact, all of Pete's workshop is in there too, so you'll be able to do basically Blue Peter it at home. But we also have a UI, like, you know, and that's part of this. And we want to be able to deploy the UI fairly regularly. There are other ways, you know. I know Pete also has a companion talk is the best way to describe it, where we can do continuous deployment to IoT devices. We're not going to do that in this talk. We're just going to go straight for, we're building this .NET app, and we're going to deploy out to an app service in Azure, and we're going to use GitHub Actions to do so. So what we have in our workflow is we've got this YAML file here that basically on every push to main or every PR that opens to main, we can go through and run this, where we check out our repo, we set our .NET SDK version to version 5, we clean everything up, we restore, we basically do a .NET restore, and it's literally that command that's running, and we tell it what directory we want to run it on, because really we only care about, for the purpose of this, doing it to our web front end. Then we do a build, we publish it, so we have a publishable package, and then from here we have our action for web app deploy, which is again something that is publicly available that you can go and look at all the code for as well in GitHub on Azure/web apps-deploy, and we pass it its app name, a published profile which hasn't had any secrets in that we've got stored against the repo, not in the repo, most importantly, and then what package we're going to deploy. Now, Pete, am I okay at this point to show the? He's not even at his chair, so I'm going to show you anyway.
Yeah, no, there I'm setting something up to the side.
Setting something up to the side, okay. Yep. So what we have here, and you can go to this URL now yourselves if you want to, is we have a robot arm. But, you know, right now we've got these 3 labels at servo 1, 2, and 3 that, unless you start fiddling with stuff, you don't really know what they are going to do. So let's change that. let's name them more accurately. So here I have VS Code, and we have Servo 1, Servo 2, Servo 3. We made a couple of changes to our code for the purposes of this as well. So we've expanded it. So we have this switch to basically allows us to disable UI elements when other folks are using things, so that we don't start sending confusing messages to the ARM and then break it. But what we will be doing is let's just make this simple change. So Servo 1 was rotation, I think, wasn't it, Pete?
Yes.
Let's change those to rotation. And Servo 2.
Sharing my screen a second, by the way, Liam.
Say again, sorry.
I'm just stopping the share of my screen for a second.
No worries, I'm not looking at it anyway.
That's okay.
So we have rotation, we have reach, we have grab. And we have made sure that Pete is sat safely far enough away so that nobody can slap him. But if I do a git add here and then git commit, we'll do labeling things properly. We'll push that up. When that goes up, if we go back to GitHub and we go into our actions, you'll see any second now. Already, there you go. It's detected there's a commit there, and that whole workflow is already running. So if I click on build here, you'll start seeing the workflow running. It usually takes a couple of minutes to run, but on the whole, this will now run through everything that we saw before. So you go, there's the setup.net. We're getting all of the output of that as well. So actually, our CI/CD pipeline is super basic in terms of how we defined it in the YAML, but everything it is doing is actually fairly involved. So that is running. I'm just going to pop this URL in the chat as well. So at some point, you may get a brief. So we're not doing anything like blue-green deploys here, but we may get a brief pause with it as it does a deploy, or you might get a brief error. But you would assume you have to just refresh the page and have that running with you. So that's still going, and any minute that will be deployed, and we'll be able to see on here rotation, reach.
Is that you, Liam, or somebody else?
That is not me.
This is normally what happens, is that people make it go mental, and then I've got to hold the blooming thing down because it will just fall over.
When we did this talk last night, it pulled itself out of the base.
Yeah, and it will try and do that.
Of course it's Johnny. Of course it's Johnny.
Yeah, hey, stop it. There you go. Oh, look,
So whilst that's running, let me just refresh this page as well. So we've got the .NET publish is still happening, and then we're into deploying the web app. So any second now, we'll be able to see the changes that we made, which is in this case is just the label changes, but it doesn't take too long at all to happen. So remember, we changed those from reach, from server 1, 2, and 3 to reach, rotation, reach, and grab in that order.
It really doesn't at the moment, the casting just doesn't work very well, from this.
For the other thing.
Yeah.
Interesting. It was all right earlier.
It was. You saw me test it.
Software PWN is on Servo 3, Johnny.
It's working. There we go.
I mean, I need to make a mad dash to swap the screen share in a minute.
Yeah. Let me just do that as well. Make sure that I'm sharing my screen again. There we go. And all of this. Select screen to share. So the screen demo, obviously, spoilers. In the I've hooked this up to a VR app.
We can see your face.
Yeah. There we are. So obviously, that if you use Unity, you can use C# in Unity, which means that you've got access to the same sort of control that you would normally. I think it's actually .NET Core in Unity at the moment, not .NET 5, but it still does Signal R. Now, with a bit of faffing, you can get the Signal R client and everything into a Unity app, which means you can also get it into something like the Quest 2. So I'm sharing my screen at the moment. I think
we'll switch back to that then, Pete.
I have to reboot the whole Quest for some reason to get that casting to work. There's a bug at the moment, it seems. But if I go to my apps and then select my unknown sources and select my third Oculus Quest app, then if everything is being shared correctly, you should see Made with Unity perhaps in front of me.
Yep. Yeah, we see that.
You won't see the blurry lenses that I need to clean, but now you should see a robot arm, and you should see it moving, and you should see the reach over there. Someone's moving the reach. But I can control the robot arm myself from in here as well, look. And it moves the real robot arm in real life.
So if I put these side by side.
Yeah, you can do that. And I'm moving the grab. Now, I've broken the grab in the app, but it is actually moving. If I move the grab, you should be seeing the grab move on the actual robot arm. And likewise, the reach, look, often falls over when I'm doing this because I can't keep a good eye.
It's not fallen over yet. It's okay.
It's amazing. People have been very nice to my robot arm. It's as wobbly in real life as it is in VR app, which I quite like. I've got a ball over there.
I didn't notice that before. That's fantastic.
Yeah, look at that. How wobbly that robot arm is. It's exactly right. I want to build that real robot arm. That'd be pretty cool to get that. Cool. But to be fair, this robot arm you can see in VR is not massively dissimilar to the one that Cliff designed. Obviously, it is. Cliff's is a lot more simplistic than this, but actually, it's quite similar in some ways. So, yeah, it works quite well. I quite like that. I see in the VR, right, you might just be able to see it graze itself out while somebody else is controlling it, so we don't fight.
Oh, yes, yes, it does, yeah.
So you don't fight over the same control.
That's pretty good. I like that. I didn't realize when we did the talk last night, I didn't spot that. That's pretty cool.
Yeah, I mean, I can go a bit. Well, supposed to be able to go a bit further forward. I can go left and right. Oh, I think I need the other controller. That's why. I can. Oh, there you go. Look, get nice and close to these things. The robot arm itself is dead cool, actually. When you get up close and personal with it, it's a pretty detailed piece of work.
Yeah, I mean, this is some really, really great stuff. So this is all operating by being connected to the same signaler hub as well, I think, isn't it, Pete?
It is exactly the same signaler hub, so that's why you can see this moving. I don't know why when I move that grab, it doesn't move the pincers.
It's moving. They're both moving.
Oh, yeah, but if I move it, it doesn't, annoyingly.
Oh, okay.
Look. So that's somebody else moving it. It's just gone down. I don't know what
yes.
I broke something.
But you can also see, conversely, the other way. I know Pete can't see that because he's currently got his Oculus on. But as Pete is doing stuff, as he's doing stuff in VR, it should be disabling the controls in the web interface as well. So there's not too much interference between the two.
How cool is that? It hurts your eyes. Really cool. So yeah, I mean, it just proves. I mean, what I want is I wanted on the other side of this table here, I wanted to have a stream of the actual arm, but it turns out that you have to pay hundreds of pounds to get a component that gives you a browser in a actual VR environment. I mean, I can get it up in the browser on here, but it's just what's the point? Because now I'm just got the same level of control that you have. So it's fine, but this is still cool to be able to move really cool. A VR robot, see a VR robot move because somebody else is doing something outside. So real world interacting with VR stuff. And I'm no VR expert either. It did take me an entire weekend to get it to work, but it's cool nonetheless. So there you go. So that's that little. What time are we? Look at the timing.
Hang on.
Absolutely beautiful that was. And here's the robot arm that you've been looking at there as well. So, but this one's disconnected, so I need to reboot it.
I don't want to rest that one. So, yeah. So thank you very much, folks, for joining us and listening to us ramble on about hobby projects where we've just tinkered, and it's we've learned a lot doing it. And every time I do this talk with Pete, I learn something new about the ARM and the Raspberry Pi and the IoT stuff. I've bought a bunch of stuff to build one here as well, so we can start doing that kind of
simultaneous driving thing.
And we've also been talking about a more advanced version of this as well, because in theory, anything that is Wi-Fi connected, you could do this with. So we've been talking about potentially building a remote control car where you could do this kind of thing, because ultimately that's, would just be powering motors, and as long as it's got Wi-Fi connectivity and connect to the hub, we could probably build a little racetrack for people to try to collaboratively race around, or go to the other extreme of let's combine those two ideas with the robot arm and this, and make a little like robot wars thing. So we'll see what happens over the course of the rest of this year. But if anybody has any questions, please feel free to drop them into the chat. But if not, you can, or if you don't have them now, you can reach out to myself on Twitter, which is @LRGulliver, and Pete is @Pete_codes. But failing that, this will probably be on our YouTube channel later this afternoon, and go and enjoy the rest of Global Azure, which is on the rest of today. I think is a bunch of stuff is on tomorrow too, and we'll see you again next time.
Thanks, everyone.